Right, so my talk's going to be oriented around Dataflow, and it's not actually entirely in production yet. It's something that we're currently working on. We've started swapping out some of our services to incorporate this, and the plan is that hopefully by the end of the year we would have completely migrated to this new way of developing our services. So before I go on, my name's Courtney, as Alice pointed out earlier, founder of Block.tech and software engineer currently attached to Haskell, Scala, C++, and Java. So they're languages that I currently use more or less regularly. Our focus tonight is going to be on essentially that, but we'll come on to what that actually means in a minute for those who don't immediately know what it is. The company that I work for is called FortyTwo Data, and our main focus at the moment, or actually the biggest part of what we do at the moment, is in anti-money laundering. We have a rules processing platform with the AML solution built on top of that. So we don't just do AML. Like I said, there is a platform and then there's a solution on top. The platform itself is very generic, and because of that and the kind of clients that we have, we end up having a very varied use case for our platform. So we have customers that have use cases varying from the kind of IoT type situations to AML, like I mentioned. And the other thing that comes with that is that the deployment scenarios vary just as widely. So you end up in situations where you're in a vault somewhere where you don't have anything other than a laptop and everything needs to work on this one machine. From that up to a situation where a bigger client goes, right, we've got several billion records and we have this cluster, we want you to process all of this and get our results back for us. So the situations in which we need to deploy our solution is very varied, and the challenge that we kind of had building up to this has been to try and adapt to all the situations that we end up having to deploy our platform in without, I guess, code changes. And that's really one of the motivating factors behind how we came to this. Now, as I mentioned, the fast requirements, it got to a point where the clients that we were getting, the situations were so different, it was really hard to always add a new piece of thing that just did that extra bit for this client. And it got to a point where we had more requirements than we could actually code to keep up with. So we took a step back, looked at what we had, and kind of decided that architecturally we had changes that we needed to make if we were going to actually continue and make the platform grow. We evaluated other architectures and other structures, methodologies, and different ways of doing the things that we were doing at the time. And we kind of went through most of them and said, well, we're not that far off what they kind of suggest doing. So if you take the Lambda architecture or Kappa, for example, what we actually have at the moment is not that far off that. The thing that we found that came probably the closest to something that we thought was really good for what we were doing was Spring Cloud Dataflow. But we are very heavily invested in the Play ecosystem. So adapting that would have practically meant rewriting most of the platform, if not all of it. So that's essentially what the talk is about tonight, and the kind of solution that we came up with for that. So there is a kind of element to this of when we started reevaluating what we were doing, we realized that actually our biggest problem was that when we got a new client, it wasn't very easy to just take out the pieces that they didn't want and drop something else in. And one of the big things about the new way we're trying to do it is to make it very composable. And in theory, it's not that new. We've had things like monads for a long time. Lots of research have gone into that, and monads are kind of the mother of composition, if you will, in software. Now, trying to do that at the software level, that's also not very new. You could, in theory, compose microservices, and that's one of the kind of things people went to service-oriented architectures for. But the main thing, I guess, was identifying the, I guess, general the general patterns that we were using and trying to abstract away from the detail so that we could easily adapt to new situations, certainly a lot quicker than we were before. Now, the old architecture that we have, as I mentioned, if you're familiar with the Lambda architecture, at the end of this, you should draw some kind of similarity to that. Now, at the far left, we've got an ingestion pipeline, and the far right, we have the UI where the user goes in and they trigger some action to do some ingestion of the data from some data source. Now, we do some pre-processing, other things on the data, and that goes into a buffer. Currently, we're very oriented around Kafka. And we then have effectively your kind of batch layer and then your streaming layer, which if you're familiar with the Lambda architecture is more or less there. And then we have our view layer. And for the moment, it's Elasticsearch. So the UI doesn't actually go to Cassandra and Spark to fetch data directly. It just gets the cache result out of Elasticsearch. And that's more or less what we have. At some point, I guess the slight variation on the typical Lambda architecture is we occasionally have to go in and regenerate aggregation. So we kind of go through half of that process again. But it wasn't very suitable for what we were trying to do. Certainly not in the last, I guess, 12 or so months that we've been trying to scale out. Now, it works in many cases, and it's worked for us for a relatively long time. And we kind of got to the point where we felt as if we were at the mercy of the frameworks that we were using. Mostly, that's Spark, because a lot of the real work, if you will, gets done in Spark in the current or old stack. It's very difficult, or at least we found it very difficult, to guarantee the performance and stability of the platform by with all the things that we'd kind of intermingled to get what we wanted out of it. And it became increasingly fragile as we had more clients, more use cases, adapting it and having all those pieces continue to work reliably. It became increasingly fragile. So the kind of things that we identified as things that we wanted, ideally, kind of fell under two main categories, predictability and flexibility. And on the predictability, the things that we wanted to always kind of be able to predict was the performance, stability, and the scale of the system. As I mentioned, you could be in a vault somewhere in a bank where you just got a laptop. You need to run the entire platform on a laptop. Or a week later, you could be running against AWS, against 100 servers. So it varied quite widely. Now, when we started redesigning this, we looked around at the existing kind of big data frameworks that you find, Hadoop, Spark, Storm, etc. And there are common principles that they all identify as being important, and essentially they can be grouped under idempotence, commutativity, and associativity. It's really difficult to achieve all three and still get the kind of scale that we need to achieve. Probably the thing, and it's relatively newish research, the thing that comes the closest to achieving all three and still scale are CRDTs. If you're not familiar, that's conflict-free replicated data types. But that's not something that's very applicable, or it would take a lot of work, I should say, to actually rebuild the platform to be CRDT-like or provide CRDT functionality. Now, the diagram I mentioned earlier, or I showed earlier, the main point of it was to show the composition part of what I'm trying to talk about tonight. We've managed to kind of agree that we can get a very long way by simply being idempotent and achieving immutability everywhere and anywhere that we can. We can go a long way with just those two. And the kind of work that we've done over the last couple of months has reflected that. Now, as we worked on this, we came up with kind of a few abstractions, or I guess the things that makes it easier for us to be able to do what we've set out to. The first thing in there is a resource provider. So you could be running it locally on a Mac, or you could want to run it in Mesos on Kubernetes or AWS. So we essentially need to be able to plug in a different provider for where we're going to get some CPU from to run this thing on. The other thing is an orchestrator, and I'll come on to why that's important in a bit. But effectively, an orchestrator, it does what it says on the tin, right? It manages what's running. It kind of monitors and says, okay, this thing is kind of going pear-shaped. We need to do something about it. That's more or less what the orchestrator does. Now, the other thing in here is an event source. And if you're familiar with things like CQRS, that's kind of where the event source idea came from. So when we looked at all these different architectures, we kind of went around and looked at all of them and went, right, that looks good, that can do that kind of thing. And we took, I think, what we thought were the best of all of them and brought them into this. And an event source is one of those from CQRS, or rather event sourcing. The other, or the two abstractions that we brought in that weren't really specific to any of these other architectures were, we started making a distinction between services and executors, because we have clients where we can say, for example, be given a budget of, they want to get the work done, but they don't want to spend a fortune doing it. So we needed to be able to say, if this thing isn't actually doing that much work, we don't need 10 instances of them. So shut them down or only run one of them. And I'll come on to why that's important in a bit. Now, the relationship between services and executors is that a service essentially provides a very thin HTTP layer where you just make a request to it and it generates some event. That's all it does. It can do some validation and so on, but it's not meant to actually do any of the real work that that thing would usually represent in, for example, a service-oriented architecture. The executor is the thing that does the work. And in the next few slides, it should become clear as to exactly what role each of these play. An orchestrator, as you can imagine, uses the resource provider to get some CPU to run some stuff on. And I mentioned earlier that it also configures and monitors services and executors. All of these generate events, and currently it's a mixture of Kafka for sticking the events in and using Zookeeper to basically create a latch. So leader election, basically, is to say only this instance is going to work on or do anything with this event. Now, the thing I mentioned earlier about coming on to, or one of the things I mentioned, was if we're given a budget to say only spend 500 per month to do this thing, we need to be able to reliably do that, because if we go over, we're going to have to be the one that essentially foots the bill, right? And we've kind of taken a SLA approach, and what you get is, or what we've got is effectively a way of creating executable SLAs. So for the moment, it's all handwritten. It's just a config. You generate some JSON that says this service needs to be able to provide this level SLA. And we've separated these out. So all the things I mentioned earlier, the abstractions, they all have their own interfaces defined, and we have multiple implementations of them. We're making use of Java's service loader. So depending on what's on the class path, it will use different things. And an executable SLA just means that we can, for example, if we have a customer that is more interested in getting things done as fast as possible, we can just have an SLA that says match upstream, which would just basically look at the rate of what upstream is producing and then match that. Whether that means spinning up new instances or doing something else, it wouldn't really matter, because the kind of monetary part isn't really the big thing. And we have currently only 2 implementations of SLAs, but the idea was that you could drop in any other implementation that you want. I mentioned earlier that actually most of these ideas aren't brand new in any way. We've kind of just been adapting and taking things out of different architectures that are relatively well known and kind of popular. Now, one other important thing in all of this is metrics. Now, we have the orchestrator, which let's go back a second. The orchestrator decides what to do depending on how each individual service in the pipeline is performing, and what it actually does completely depends on the implementation that's on the class path at the time. But I'll go through the next diagram that prematurely went through just then, and it will make more sense after I explain that. So the new architecture is kind of like this, where we've got separation, as I said, between services and executors now. You kind of always need your services on, because that's the thing that accepts requests from users or from any other source that they might come from. So we have our service always on. The kind of flow is similar to the old one, where the UI just makes a request to this service to say, all right, start an ingestion from this data source. It might be a URL, a file, or database, or whatever. What would then happen is it would, instead of start doing the work, it would actually generate an event. And in the middle of all this is where the event sourcing plus the lock-in comes into play. And as I mentioned earlier, we're using Kafka at the moment for pushing our events into, and the lock-in is done by Zookeeper. The orchestrator sits in the middle of all of that. Now, I mentioned earlier that your service, it's really only for validating stuff, so very lightweight work. Shouldn't actually really do anything that will take a lot of time. The orchestrator and actually everything in there uses the event source, so Kafka in this case. I've skipped most of that because the diagram would get very messy if I included all the lines. So just imagine that every box that I put on there actually produces events as well. Now, the flow changes slightly. At the moment, because we've not completely replaced the entire pipeline yet, actually the only thing we really needed was one Kafka buffer at the start, after we start generating or ingesting data rather. This is true, and I'll explain why in a second, and this is where Akka Streams comes into play. We adopted a reactive model because actually guaranteeing the SLAs, we needed greater control over when we actually took data, because you don't want, for example, if we started subscribing to a WebSocket stream to get the data, that upstream would just overwhelm downstream, and then you end up in a situation where you've blown the budget, for example. So we needed control over when we said, right, let's get the next one. And that's one of the good things that Akka Streams actually brings to the new setup. Now, we have one buffer at the moment upstream, that's just Kafka. We push into that from the ingest executor or executor. And I'll keep reiterating this, but there is a clear distinction between the ingest service and the ingest executor. A service literally only just it does some validation and generates an event. And the executor is the thing that actually goes off and does any real work. The rest of the diagram, you'll start to notice that instead of pushing, because obviously from the ingest executor, Kafka won't automatically pull your data, you have to push that into Kafka. But everything else downstream actually pulls when they're ready, and only when they're capable of handling the next piece of data. The rest of the platform, we haven't completely migrated, but leading up to Elasticsearch and Cassandra, we've written some Akka Streams flows for them. And what actually happens is that as you go downstream, unless, for example, the Cassandra executor pulls data, nothing happens upstream, so the data just stays in Kafka. So you have to start pulling downstream for anything upstream to happen beyond that buffer, and that's mainly why the buffer is in place. The rest of the flow is similar to the old architecture. Now, that might look worse because you suddenly have like these 10 other things going on. It looks more complicated, right? But you can literally write an executor that is no more than a function, because all it needs to do is inspect some data, maybe do something with it, change something, add something into it, and that's your executor. They are very small, and that's kind of the main idea. They're meant to be composable. You're meant to be able to say, oh, actually, this client doesn't want that. Let's just quickly write a function or something to replace that, drop that in, and suddenly that's all you need. You don't need to go off and create a new service, which might take a week or something, well, depending on what your life cycle is. But it gets a lot easier to plug things in because they're a lot smaller. It's also a lot easier to test them as well. Now, it does look very panicky when you look at the diagram and trying to understand or keep track of what's happening, where events are coming from. But actually, you don't handle most of those events. When you write an executor, your function, so the API that you get is just you provide a function that gets called when something happens, and you decide when to pull the next thing in, and that's it. Everything else gets handled by the libraries that we've written around it, and the orchestrator, I should say, handles all the eventing and scheduling. You generate configurations to say, this service has this SLA. Currently, I mentioned we've only got 2, but you start to get the ability to be able to, using JSON, which isn't great for composability, but using JSON at the moment, you could literally just go, all right, this service connects to this service, and that's all there is. If a customer comes along and doesn't like that or doesn't need that functionality, you just change the configuration, and that's it. It's a much easier conversation to have when you're in a meeting and you just say, well, okay, we don't currently do that, but give me a minute. And you change it on the fly, and that's it. Whereas before, we would have to say, okay, that might be a week, 2 weeks, a few more weeks, or whatever. It's a much easier conversation to have. I included this to try and give you an idea of kind of how it all strings together, but it started to get very messy, so I stopped. Now, this mostly just covers what I explained before, but actually, if you look at down here, the important part is this very last event here. So the idea was that you were going to, if you're familiar with the Twitter garden hose, they provide a sample of tweets that are going through Twitter. And the idea was that I was going to walk you through building essentially an entire pipeline to process that. Now, at the very end, you've got this domain exec, but this would essentially be something that you've written. Now, the important part is this pull n. And this is where the very last service downstream basically says, I need this data, or I'm ready to accept more. And it starts pulling. And unless that happens, most of these other pulls, not most, all of these other pulls, none of them actually happen until that very last thing downstream says, okay, I'm ready, give me the next one. The important thing that the orchestrator does that I might have missed from the last slide, or several slides ago. The important thing that the orchestrator does is it will look at what or how services are performing. So it will look at an executor, and depending on the SLA that's been configured for that service, if, for example, it's got the match upstream, and your current executor is doing, I don't know, half the rate of what its upstream is doing, it will say, fine, go to the resource provider, can you provision another one? Yeah, okay, let's provision another one. And it will leave that, watch the metrics, and until it meets the SLA, it will try to essentially spin up more instances. And once the load goes back down again, it automatically scales it back down. So you end up in a situation where you define your scalability by just configuring the platform to grow how you want it to, which essentially, well, I say essentially, but that makes it a very powerful thing, because now we don't need to write code to be able to guarantee or provide all of these guarantees. And that's one of the things that was really important to us. I was planning to animate this slide, but actually we went to the pub and I didn't bother. That's more or less it. I wanted to provide or do some code examples as well, but it was really hard to try and cram all of this stuff in and still try and get it within 15-20 minutes and leave time for questions at the end. But if I didn't, I haven't been booed off stage yet, so I'm assuming I could come back another time and maybe do a more practical walkthrough and show you guys some of the interfaces and how it all works, and probably do the Twitter streaming example as a real thing. But yeah, and that's it.